Okay, let's go and take a look at lesson 5.5, substitution. So we end our course with integration techniques that allow us to integrate more complex functions or functions where we can identify a composition of functions similar to the chain rule. So it's kind of like undoing the chain rules we're looking for. So when we look at an example that first emerges here, and we'll do some extra examples beyond what's in our textbook here. But as you see the integral here, which definitely looks more complex. And so we can't use some of the techniques that we've had. You may have been able to expand out the cube and then distribute the 2x. That would have been one way to do it. But what emerges is what's called the substitution for indefinite integrals. It also works for definite integrals, which we'll look at later. You are going to see a process. And again, it's kind of like the chain rule, the derivative of the inside, right, emerges. So let's look at an example of what we're doing. So that original function here, what's the integral of x squared minus 3 cubed times 2x dx, right? So what we're looking for is some function inside of another function, and then we substitute, we rename it with some variables. It's what we call change of variables. And this change of variables, for those who go on to Calc 2, becomes a technique we use to solve differential equations and involved in other areas where we do these substitutions. It becomes very helpful to recognize them. So there's a strategy in going about how to integrate something like this, right, where you look for some function inside of another function, and the derivative of that piece is also apparent. So for example, in this 5.30 example, a 3x squared plus 4, the derivative of that is 6x. So you'll see this function and its derivative are in the original function, right, as we see those pieces. And so what you're going to end up doing is, you see, you're going to say, okay, I see this inside piece. I'm going to, and you can use any variable, but u is the common variable we use. It's called u substitution. Let u equals 3x squared plus 4, and then the derivative of this du, right, is 6x times dx, right? So kind of that idea that we've used previously in terms of taking derivatives, implicit derivatives, right? And so then what happens is this expression right here becomes this here. Those are equivalent expressions with the u substitution. Now I can integrate this u to the 4 du is u to the power 5 or 5 plus c. And then you resubstitute back in what was u. U was 3x plus 4. And so we have our integration. So just again, take some practice going through the different examples that are there. Now, it's important to realize that you can go ahead and check your answers right wherever the example was, right? You can go ahead and take the derivative. That's it. Check your answer by taking the derivative of your integration. If you take the derivative, it should produce what was inside the integral, right? It should be the integrand. So again, being able to work back and forth. So all you have here is a whole bunch of different examples to go through. You can take a look. I'm going to do a few extra examples to show you different than that is here. Something that emerges, that comes out, is the substitution for definite integrals, right? So it's the same process. As you can see, we would end up with the same result. The only difference is, as we look at like an example like this one here, right? You have this expression, and we use u substitution. You're changing variables. So originally we were integrating from 0 to 1 when x is 0 to 1. But now when we change the variables, when we integrate, notice it goes from 1 to 3. It changed because these were x values, and now we're integrating with respect to u. And we learned that u is equal to, on this problem, u is equal to 1 plus 2x cubed. So you go ahead and you substitute 0 and 1 in here. You plug 0 in here, you get 1. You plug 3 into here, you get, you plug 1 into here, you get 3. And so that's where your new limits of integration come into play. And so you end up with this here. Now, once you get to this point right here, once you get to this point right here, some people prefer just to change the variables back to where we were. Once you get to, let me see if I can write down. Once we get right here, right, and then you end up with u to the 6. end up with u to the 6 over 36, right, from 1 to 3, right, when you expand that, right, when you do that. Some people just change it back. Oh, I know what u is. Again, but you see it looks simpler to evaluate here. Some people go ahead and put that back in and say what u was from our beginning, u was 1 plus 2x cubed. So really what this is 1 plus 2x cubed over 36. And then you can go back to the original limit. So that's another way to think about it. So you could keep it this way or go back and plug into the original expression. So just keep that in mind. That's possible. You may see that as you're doing and looking at other videos and going through things that you may see that. So keep that in mind. Okay. So so it works the same with definite integrals. You can then evaluate with the u substitution that allows you to do more complex things, right? So here are a couple of a few other examples I wanted just to pull up so you have a chance to look at others that are completely finished and done already. So here are, I have 4 of them here, and you can pause to see if anything unique. There's some description here, but you, again, when you see these look really complex, and then you start to play the game and start to look for what's my u, and sometimes you choose the wrong piece, but I start to see them in pieces, right? Here's one piece, and then here's another piece, and you start to see the different pieces, and then your choice of u and then du must occur in here, right? If you would have chosen u to be 8y minus 1, the derivative of that is 8, and then somehow it still doesn't work out for us, right? So you can see that choice is very important. The change of variables occurs, and then you can integrate, and then you substitute back in. Again, it looks pretty easy, right? Now that you see some, here's another one. This is similar to the one we saw earlier with when you have these two. You could expand this and then distribute and then integrate. That may be, but in this case, I see the derivative of this turns out to be this, which, again, if you look carefully, negative 30 is not in here. And so a subtle thing that has to happen is that when you rewrite this, I'm trying to rewrite x squared dx, right? So once I had du equals negative 30x squared dx, here's my u to the power of 4, and then I have x squared dx, but I have negative 30x squared dx. So the way you figure that out is you solve for x squared dx, and you get negative 1 over 30 du. And so take a look at how this substitution then emerges, right? Now we have, now we can do the integral. There's your, right? And so when we make that substitution to the x squared dx, you'll see the negative 1 over 30, it then occurs here. It's part of it. So this happens often on these integration problems with substitution. You have these constants, you have to worry about that. Like it looks perfectly, it's like x squared and dx, but I have a negative 30. Well, the way you get rid of it is with its reciprocal, right? And you can see when we solve for that, those components, you'll see within where the substitution. Some people like to take this and then move it out over there so that you end up with negative 1 over 30 integral u to the 4 du, right? So that negative 1 over 30 stays out as you then integrate and figure that out, 1 over 5 u to the 5, and then now, right? So keep that in mind that, again, you'll see different ways of doing that. Let's see this one. Here's another example of that situation, right? A more complex one. Your u is that, your du, but I don't see negative 8x. I do see x dx, but I don't see negative 8x dx. So when you solve for that x dx so that you can rewrite it, that x dx is negative 1/8 du. And then here you can see a good example of bringing out that constant. So you end up with u to the negative 1/2. And now you integrate, and then that comes part of the solution, right? U to the negative 1/2 is a 1/2 u, right? You integrate that. And so there's your, it's 1/2 u to the 1/2, right? Add 1. And then, but that 1/8 is going in back into there as you try to integrate that, right? So you get negative 1/8, and the integral of this, right, is 1/2 u to the 1/2. Sorry, not 1/2, it's 2u to the 1/2, right? Because when we take the derivative, going back and taking the derivative, you can see 1/2 times 2 is 1, right? Remember, going back and forth as you do that. And then when you distribute, you get that it was 1/8. So keep that in mind as we, again, that constant plays a role in our integrals. And you can always, again, take the derivative and see if it takes you back to your original. And then here's one with tangent. And so same thing, this constant pops up in secant, right? That relationship, let u equal 3 minus 4. 3 minus tangent 4t, take the derivative, and it's not perfectly, I see secant squared 4t, there's a -4. And so again, that -1/4 happens over here, and then you could integrate again. So keep that in mind, that constant pops up.